Hello everyone, I'm Claire, and today let's talk about the second part of how does the Taylor series actually work. And so let's talk about the second part, and today we're going to talk about the sin x and the cosine x. So first we're going to talk about we focus at 1 and we calculate power 2, and this function is sine of x. And this is its derivative function, so it's cosine of x. And we think about 1 to power 2, Actually, we focus at 1, we calculate the power 2. And so right here, so we have this is our original figure, and so if we write it out just like this and so on, right? And so the first term f of 1 is this value, so we don't have it intercept if we say it's a sine x, so we don't have it intercept. So right here, we probably just have this value, we don't need plus anything else. So right here, just this value, f of 1, and we say this one. So we use this one. So what's this? Okay, let's see. This is the value right here. And we plus the x minus 1. Plus the x minus 1, actually it's power 2 minus 1. So we have this rectangle area. Okay, so we have this rectangle area right here. This angle. Okay, so the second part, the third part right here. So first we have a speed right here, because this is actually negative sine of x, and this is sine of x. This is negative. So we can say first we have a negative value from 1 to power 2. See, we have 1 power 2, and we have a negative value, and we calculate its area. Right, we just use this value. We times x minus 1, and we times x minus 1, so we have this area. You see, this is negative. So if we say to the next part, so it's it's original function. Okay, so the original function is a negative area of it's a triangle, right? And we also calculate this area because we times x minus 1 and times another 1 over 2, so we have this area because it's the 1 to power 2. Okay, so right here is just this triangle area. Let me see. Good. Alright. It's like this, okay. Alright, so now right here is just this triangle area. And, alright. Okay, so the next part right here. Okay, so let's think about certain parts. So right here it's also negative, so it's a negative cosine 1. Okay, so it's also negative. So first we have a negative value, and we calculate area. And right here, this value, and we calculate this area. So now it's this part, and we will times these two guys again. Okay, it's 1 to power 2. Okay, so this area right here is just something like this, and this is a coordinate function. Okay, so now let's think, where is this coordinate function? So we know if first we have this area already, so our original aim is to find out this whole thing. So actually, now our aim is to find out this part. So now, if we minus this part, the triangle, so we have left this part. So what's the next step? I'm going to minus this, right? So if we minus this and we have this part, and we minus this part, so where is it? And if you calculate it, you will know it is less than our aim now. So it's inside this figure. Maybe something like this. Good. Like this. Okay. And so what's the next step right here? Alright, let's think. Plus this part is less than the aim. So if we plus the next part again, so it is still less than our aim. Of course, we know the next part is positive, because the next part, it is sine x, right? This part is sine x. that part is sin x. So and times blah blah. Okay. So that part is positive, and then we plus a value. But if we plus this value, even plus this value, it is still less than our goal. Okay, the aim. And if we plus again one term, then it's greater than our aim, because right here it's different. It's sin x. So we just so it's derivative. So first our original function, positive, negative, negative, positive, negative, just like this. But first, neighbors of them are positive, and then neighbors of them are negative, and then neighbors of them are positive, blah blah blah, and so on. So something like this. Okay, just like this. Okay, so it's positive two terms, so it's greater than aim, just like this. Anyway, we're not sure if this guy, if when you plus or minus a term, it is less than our goal, you can say aim, or it's greater than it. But it is always approaching to our aim, or can say goal. So if it's a sin x, so let's see if it's a cosine x. So it's a little bit hard because we can think about if we focus at 0 and we calculate what? We calculate. Let's see. We calculate power 2. Sorry, we calculate pi. Okay, so we're going to think about cosine x, and it's 0 to pi. Good. 0 to pi. Okay, so let's draw the original function. It's 1, 3, middle. Okay, it's like this. Cosine x and this x. Okay, so original function, our aim is to find this value. Okay, and so first we have this value. We don't take because we can't see this in a derivative function. Okay, so let's draw the derivative function right here. Okay. Alright. Okay, measure that right here. Okay, let's think. So now, it's like this. Okay. Position 1. Okay. Okay. So now, all right. Now let's see. Let's write out the function right here. Okay, and the function right here. So first, it's 1 minus 1 over 2x squared, and then plus 1 over 4x. Sorry, and we have a factorial and x. 4, and then we minus 1 over 6 and factorial and x to be 6, and then we plus 1 over 8 factorial, and then x3 8. And then we minus 1 over 10 factorial and x3 10 and plus so on. Alright, so when you write another its derivative, so it's negative 1 x, and we plus 1 over 3 factorial and x3 is 3, and then over and x3 5, and plus 1 over 7, okay, and I want to use 1 over 9, x3 9. Alright, and then we plus so on. Alright, so, okay, right here. Good. Okay. So right now our aim is to find this area. Okay, so first we have a triangle because it's negative x. Okay. Okay. First we have triangle after the linear equation. Okay. So next part right here is this one. We see this one. It's a cubic function. So, and actually we calculate right here pi, and we calculated it's a phi. It's a phi. So good. Now this one is this function its own. So if we plus it with this function, so what do we have? Right here we have a 2. Good. Okay, so if we plus this term again, so this term is only, actually it's very slow. So we're going to write it like this. it's like this. I don't do it really good. Okay, so if we just put this and with this together, so we actually it is like this. Right, like this. Okay, and so next thing, and right here, the lowest point is always getting closer to our aim right here. It's -1, right? It's always getting closer to this one. And if you plus to this term and the value right here, the y value, it is 0.0, 0.9, blah, blah, blah. And if you put this term, then it just turns to 0.6, blah, blah, blah. And if you put this term, then it's 0.99, blah, blah, blah. And just so on, it's always getting closer. It doesn't mean it's getting back something, but it's always close to -1. And that's our aim. Okay, so the next thing, let's think about the original function, and we're gonna think about the behavior right here. If we have a 1, and if we minus this guy, so we just draw this. This is 1. Okay, and if we plug in. Okay, and then so now the next thing is if we plus another term right here. So if we compare the quadratic equation, so if we compare the two functions their own, and who's much more faster? We know there's a property. If we just compare it from 0 to 1, so of course our coordinate function is faster, and so we just have something. It's getting faster, so it's still getting smaller, and from 0 to 1. But after 0 to 1, you see, if you draw a picture of it, it's still getting less. But what happened? Because we have a 1/4 factorial right here, so the increment, so from 0 to a value, it's a greater than 1 a value in this period. The increment of xt4, this function, it is less than the increment of the coordinate function, that part. So, but because xt4 is terminated positive, so we still have some increment right here, positive increment right here. We just have plus some value. It is bigger. The value is a little bit bigger every time than the original, the graph right here. Okay, and so after the point, the value, as I say, of course you see, and the increment of xt4, this function, it is greater than the increment of the quadratic, that part. So it just looks like something like this. So we have here 0, and we get it. So something like. All right, so now we have if we plus the third term here. So right here, this picture, and the third term just look like this. Okay, so now we're gonna plus the fourth term right here is xt6. So we have a 1/6 factorial right here, and it's a little bit slow, but you see, we have a 1 over 6 factorial right here. So from 0 to a value more, maybe a value more than, it's a value more than 1 in this pair, and after this point, x6 this function is very fast. This function is always getting down. Okay, and so if we go back and we see this function actually for this function like this, and so of course, so right here we're gonna find the lowest point right here. So we're gonna find the lowest point, because right here in this problem we have a lowest point right here. So let's think about it. If we can think about it, if this function and this function, we plus them together. So let's think about it. If we want to find the lowest point. So if it's a low point, we know the two slope of, if we choose the same x value, they need to be contrapositive, just like a slope is first. One slope is like this, so it's this over this, and so we times the dx. So if we times the dx, we have a dy value, dy increment, and it's totally opposite. This, so it's contrapositive. Okay, like this. So it's this over this, and then you times dx, so you have a dy value, just like this. So, and this is positive, and this is negative. So if you plus them together, that's 0. Okay, so that's the lowest point. So we know when it's the lowest point, these two speeds need to be contrapositive. So let's think. Of course, so and because this function is always getting down, it already gets down some-time. But you see this guy, it is just get up. So, and another reason is we see x6, this function, of course its exponential is greater than this function. Of course, it's actually for this function. Of course, this guy's exponential is greater than this guy's exponential. So, of course, x to the 4th function can never catch up to the x to the 6th function. Okay, so we know, and so right here right now we know this function didn't have a lowest point. Actually, we don't see that's a lowest point, because for those functions, like for x to 4th function, you see we can say that's the lowest point. But right here, we can just say we're gonna find the point that the slope is 0. We don't include this one. Okay. So and let's think, if we just plus 1 over 8 factorial x to 8 this term, so and this function will turn to like this. It's a little bit same like x to 4 this part. So, and if we plus another x to 10 this term, you'll actually find out like this. Slope is 0, and then, okay, we can say it's flat, and then go to flat again, and just get down. So, we can say right here, you see, if we plus 2 here, you see for this Taylor polynomial right here, if you just plus to this term, it just look like this. If you plus the 3rd term, it just look like this. And you plus to the 5th term, still like something like similar like this. And so if you plus the even terms, this term, or plus to this term, plus this term, it just change like this, and we change to this, and we change to like this. So it's always getting a lot of flat point. A lot of point that the slope are 0. So we can say these are the even terms of this Taylor polynomial. You see, it is always getting a lot of flat, or we can say the point that the slope are 0. Okay, so we can think, when after some terms, if it's the even term, okay, so just like this. A lot of point that the slope are 0, like this, and then just kind of get down. Okay, so if it's infinity term, so again, approaching cosine x. So if it's infinity term, it's just cosine x. So cosine x, it is always flat, right? is infinity, then we don't get down or get up, get down, just like this. Okay, so this is how we're pushing this function. Okay, so this is today's video, and we just talk about sine x and cosine x, and from if we calculate pi over 2 or calculate pi.